Thanks, Trevor. Hello, everyone. Thanks for joining the session. So my name is Sergio, and today I'm gonna talk a little bit about how to debug an embedded Linux device with the Yocto project and Open Embedded. So yeah, let's start a little bit about myself. I've been designing embedded software for 25 plus years, from small microcontroller projects to big multi-processing systems with embedded Linux. I've been working with my company here in São Paulo, Brazil for several years. And for the last year, I've joined Toradex, and I've been helping them developing a distribution called Horizon Core. I'm an open source contributor, and sometimes I write a few technical articles on my blog, embeddedbits.org. Yeah, let's start. We don't have much time. I really want to do some hands-on in the end of this session. So let's see what we can do. I'm going to start with a quick introduction about debugging, but very quick because I want to focus on how can we improve our experience on debugging an embedded Linux device with the Yocto project, and hopefully some hands-on in the end of this session. So before we start, it's worth mentioning that this talk is not about debugging bitbake or metadata like recipe classes. This talk is not also about debugging build problems, and also not about explaining how the debugging tools work. So I'm going to really focus on tips and tricks to debug an embedded Linux application or the kernel using the tools provided by the Yocto project. That's the main idea here. A little bit about debugging tools. Usually, one of the main techniques that we use to debug software is adding prints to the software, right? That's not bad. It is only bad when this is the only tool that you have in our toolbox. There are several tools out there that we can use. Sometimes adding prints to the code is a good technique, and a fancy name for this technique is tracing. So you are tracing the execution of your application with your own print messages. But there are several other tools and techniques that we can use to debug software, right? We can do analysis of core dump. We can do debugging interactively, like using a debugger like GDB. So there are several different technologies and tools and techniques to debug software. I had a talk that I've done a couple of weeks ago at the Embedded Linux conference for those that are interested. I think it's called Linux kernel debugging going beyond print K messages. Although it's kind of focused on debugging at the kernel side, there are some insights in that presentation about the general view of tools and techniques to debug software on Linux. I can also say that there are kind of three main approaches for debugging. You can debug directly on the target. That's one way to do it. But sometimes that's not possible because the target may not have the resources needed. So you can install debugging tools and like applications with debugging symbols and the source code and all of these that you need to do debugging. So sometimes that's not possible or that's not feasible. The other way to do debugging is remotely. So you run the application on the target and you debug on your host, and you have some kind of connection with the target where you control the execution of the application. That's another way to do debugging. A third way would be what we usually call post-mortem analysis. That means you run the software on the target, you collect information about the execution, and you do the analysis on the host after you run the application on the target. So, for example, you generate a core dump file on the target, and then you do the analysis on the host. So those are three kind of different ways to do debugging. And of course, it really depends on your use case. Sometimes you have the access to the targets, then you can do remote or local debugging. Sometimes you don't have access to the target, you have to request someone information like logging, acquire the file, then you do a post-mortem analysis on your host. So it really depends on your use case, the way you're gonna do the debugging. Now, what you need to do debugging, you're gonna probably need a few artifacts to debug the application, and also, of course, tools. My view is that we need at least those 5, depending on the need. We may need all of those 5 components to the debugging. First one, source code. Especially if you are doing interactive debugging, like you want to run the code step by step to understand what's happening. You're gonna probably need the source code for that, right? Because you don't want to step by step on assembly. The other thing that you may need is debugging symbols, and usually that's mandatory for debugging, especially because again, you don't want to understand what is the address means. You want debugging symbols to convert addresses to variables and functions and file names with lines and all of this. The third thing that you may not want when debugging is optimizations. Optimizations sometimes, not always, but sometimes may impact the experience during debugging. Again, if you are doing a step-by-step execution of the software to understand what's happening, if you have the application compiled in an optimized way, the source code will not match the binary, and that's a problem, because when you do a step-by-step, you're going to see your code jumping from here and there because the binary doesn't match the source code anymore, because the compiler optimized the binary when compiling the code. The fourth thing that you may not want during debugging is some kind of security mitigations enabled by the compiler. And that's more usual right now for distributions to enable this when compiling software. For example, this is default when you build a Pocky-based distro. We're going to discuss about this. We're going to have some flags enabled in GCC to improve the security of the compiled binary. For example, the address space layout randomization will be enabled. And of course, when you run your application, and every time you run, you're going to use different addresses, you're not going to be able to easily convert those addresses to symbols in your source code. So that's another problem that you could have. And last but not least, tools. Tools are a very important part, of course, of the debugging process. And you're going to probably need a lot of tools depending on the problem that you are facing. So right now, we're going to talk a little bit about all of those topics and how that relates to Yocto. So source code. As I mentioned, you're going to probably need source code if you're doing an execution step-by-step with GDB. So how can you get the source code of the application you are debugging? Here, it depends. If you are doing debugging remotely, that's not a problem because you have the source code in your build directory. We're going to discuss how can we like having this more centralized. For example, generating an SDK, you can have that. But if you're doing debugging on the target and you need source code on the target, then you can install the source packages. So for those that work with Yocto knows that OpenEmbedded Yocto will split when a package, when a RESP is processed, the result will be split in several packages, right? One package will have the final binary, the application, the library, and then we have separated packages with the debugging symbols, with the source code. So if we want to install the source code on the target to do debugging on the target, we can just install the source packages. There are two approaches for that. We can use the image feature source packages and install all of the source code there. Usually that's not required, but maybe if you want to step through like code of libraries, all of this, maybe you may want to install everything. But of course, keep in mind that it will increase the size of your image. Now, if you're just debugging on a specific application, you can just add the source code package of your specific application. Don't have to add everything, right? So you just installing the image. Like in this example, I'm installing the source code of BizBox in the image. Debugging symbols. So again, debugging symbols is one of the most important things that you may want during debugging, because you will want to convert addresses to files and line numbers and functions. And for that, you need debugging symbols that are basically some dedicated entries and sessions in the ELF file. On Yocto, you can have the debugging symbols on the host or on the targets. On the host, I'm going to discuss it later. You can build a debug file system, or you can generate an SDK. We're going to talk about that later. But if you want the debugging symbols on the targets because you want to debug on the targets, for that you can install the DBG package of the application or the applications that you are debugging. So that's very easy. You can just install all of the debugging symbols from all of the packages that you install in the image using the image feature debug packages, or you can just install the debug packages of the application that you are debugging, just adding to the image. A third option that's usually not necessary, you can just disable stripping the binary, and then you're going to have the debugging symbols there. So you can use the inhibit package strip, but usually that's not required. I usually install the debugging packages if that's what I need in the target. Remember that if you are doing remote debugging, you don't need the debugging symbols in the target. You will need the debug symbols only in the host. So if you are doing remote debugging, don't need to worry about installing source code on the target, installing debugging package on the target. There's no need for that. Optimizations. Again, if you are running the code step by step, you can have problems with optimizations. So on the Yocto, there is a variable called selected optimization that may contain the content of full optimization or selected optimization, or debug optimization. So and basically you switch. By default, it has the content of select optimization that by default will optimize every compiled code because of the -O2 flag of GCC. Now, if you want to disable optimization, you can use the debug build variable. If you set it to 1, then it will use this debug optimization variable, and then it will pass the GCC -OG. Then the application will be built without optimization. I also usually don't use debug build equals 1 when I'm debugging something, because it will optimize, it will rebuild everything without optimization, and usually that's not what you want. You just want to debug that application without optimization, and rebuilding everything is not that good because we're going to have to wait a lot of time. And sometimes it's rare, but sometimes it happens that when you debug something without optimizations, you get into bugs, because usually the developer just tests the applications in a few ways. So sometimes the developer didn't test the application with optimization disabled, then you can get on some weird bug like race conditions, things like this. So usually it's better if you are debugging an application, just use, you can use an override and then just disable, just set the debug build variable only for a specific package, a recipe that you're building. You don't need to disable it for everything. So in this example, I'm just I'm going to rebuild BizBox with optimizations disabled. The last important thing about building applications that is ready for debugging is security mitigation. So as I mentioned, some security mitigations may impact debugging. For example, there is a GCC flag called PIE, P-I-E, that will enable basically address space layout randomization on generated binaries. And then every time you run the application, it will run with different addresses. That's good from the security point of view, but that's not good from the debugging point of view, right? A trade-off here. So you may probably want to disable it if you want to debug on a specific application. So that's what I'm doing here. I'm for BusyBox again. You don't need to disable it for everything, right? Because it will rebuild everything, and then you're gonna have to wait. You can just disable it for the application that you are debugging. So here I'm using override again to disable it for BusyBox, and I'm using this variable that has the flags that disables this option. And tools. Now, if you want to tools in the target, you just install in the target, right? So if you want to do GDB in the target, you just install GDB in the target. If you want GDB server, just install GDB server. So no secrets here. There are some image features that can also help. For example, the tools debug that will install the GDB tools and also some tracing tools, mtrace and strace. That is the tools profile that will install some profiling and tracing tools like perf, editng, valgring. So I think there is no secret here. You just install. If you want some tool in the image, you just install in that image, right? Now, if you want to do remote debugging, then you will need basically two things in your host machine to do remote debugging. You need a sysroot of your image. That's basically a version of your file system with the applications and the debugging symbols and the source code. So you can do debugging. That's one thing. And the other thing that you probably need is debugging tools. So a sysroot with the applications with debugging symbols and the source code, and debugging tools. That's basically your tool chain with the debugging tools like GDB, ADDR to line, and things like this. That's probably what you need to do remote debugging. I think we have a few options here. One of the options would be to generate a debugging file system with those two variables. You can do this. Basically, if you enable these two variables, you can do this in your local.conf, and then during build, it will generate another file in your deploy directory with a stripped down version of your root file system with the applications with debugging symbols and source code, so you can debug it. But you don't have the tools here, only the stripped down version of your root file system prepared for debugging. Then if you want the tools, you can, for example, run meta toolchain, and you can have the toolchain there without any sysroot. But then you can mix together the tools from meta toolchain with the debug file system, and then you can have an environment to do remote debugging. I do not do that. Usually, I generate an SDK. I think it's easier, although it takes a little bit more time. I think it's easier, so I just generate an SDK for my image, running the populate SDK task, and then it will generate for me a shell script that I'll run, and then it will install in my machine all of the needed sysroot with the debug and source packages, and also the tools there. So everything is going to be there. Usually that's what I do when I want to do remote debugging. Nice. A few words about kernel debugging before we do some hands-on. There is not really much to talk about kernel debugging when we are working with Yocto. Basically, what you may need is change the kernel configuration to enable some debugging options, so you can do debugging, right? That's basically it. And then you may need tools, of course, and then probably you're gonna use the tools from your host to do remote debugging on the target. You may, for example, want to trace the kernel with ftrace, then you're gonna need to install ftrace on the target. So there is no secret on kernel debugging with the Yocto. So, for example, if you are if you want to debug the kernel, you're going to need to change the configuration. So if you are using the kernel Yocto class, you can generate a kernel config fragment with the debugging options that you can enable when you want to do debugging in the kernel. But you may probably want to disable it for production images. One important option in the kernel for debugging is the config debug info. That's very important because it will compile the kernel with debug info. So if you want to do symbol resolution of this in the kernel, you're going to probably need this option enabled. And of course, there are several options in the kernel. There is a menu there, kernel hacking. If you go there, you're going to see several options that you can use to debug the Linux kernel, from tracing to some kind of frameworks to identify like locking, hangs, memory leaks. It's very nice. If you want to know more, go to this menu and learn the options that we have there. Very nice. So that's all about the presentation. So basically, we discussed this here. What we need to do debugging, right? Source code, debugging symbols, applications compiled without optimization, without security flags, and the tools, right? And we discussed a little bit about how can we do this with Yocto. So I have right now almost 10 minutes, a little bit less than 10 minutes. I have here a few demonstrations. So let's see what we can do during this final part of the presentation. Hopefully you all can see my terminal.
Yep,
so
looks good.
Great, thanks. So what I have here is a build directory. I created a small layer for this presentation. I created a few patches to generate bugs, so we can debug those bugs, those patches here. I just changed the GDB configuration to enable TUI mode. That's a very nice UI mode of GDB. And I also enabled some kernel options for debugging, especially the config debug info. I don't know if we're gonna have time to go over the kernel part of the hands-on, but let's see. And I have here a small device from Tradex running a small distro that I created. And I added a bug in this application, fping. It's a kind of ping that is able to send SMP packages to multiple devices at the same time. It is working when you run it like this, but when you run like this, seg false. So how can we debug this? Let's discuss about this right now. There are a few options that we can use here to debug. So one option is let's generate a core dump, and then open this core dump and see what happened. That's one way. The other way would be let's run step by step with GDB and see what's happening with this application. So let's first start with core dump. Let me first erase here the core dump files that I have here. So I'm gonna enable core dump. And again, I'm not go over the details of the tools here. I'm just gonna quickly explain because we don't have much time. So I'm enabling the generation of core dumps, and then I'm gonna run the application again, and it will segfault. And now we have a core dump file right here. So I can debug this dump file in the target or in the host. Let's do both here and see what is the difference. So let's see, I want to debug this in the target. What do I need to enable it in the build to do this? I have here a few comments just to show you. So those are the three options, right? So what I want to do here is use GDB to open that core dump and identify the line of code that generated that segfault. So for that, I need at least to enable those three options. I need to install GDB because I want to do this with GDB. So I'm installing GDB in the image. I want to install the debug packages to do symbol resolution and the source packages so GDB can open the source code and see what's going on. And I also want to disable the PI flags so I can do symbol resolution, right? Because without this, I will not be able to do it because the address will be randomized. So those are the three options that I needed. And then with this, I can go to the terminal in my device. I have already, of course, I'm not going to build this here because it will take a lot of time, but I have already done this. And then here I can just, first I can show you. So when you enable debug packages in the target, you're going to have the user source debug directory with all of the debug packages enabled. I can also show the file with debugging symbols. So this is the fping with debugging symbols. This is also needed for proper debugging, right? And the fping command is stripped, so we can see here both of commands with and without debugging symbols. Then I can just go to the source code of fping, see that I'm in the target, right? And then I can just run GDB there. So GDB, I want to run with the TUI mode. This is the binary that I want to debug, and this is the core dump. So if I do this, oops, yeah, I think any curses is going crazy here. I don't know, maybe because, I don't know if it's because of the size or if it's because of me sharing this. Oh, yeah, now it's better. So I just opened the application with GDB, giving the core dump file, and you can see here, right, the line of the source code that caused the crash in the application. I can do the same if I want to do remote debugging, but of course, for remote debugging, what I need to change in the application to build the application, just this. That's the only thing I need to do because I don't need GDB in the image. I don't need debugging package in the image. I don't need the source code in the image. I just need to make sure that the application will run with the same address so I can do symbol resolution with the binary. So that's the only thing that I will need to do remote debugging with fping. I can quickly show you how that works. So I have the core dump on my device. Actually, my device is booting via NFS, so it's in the network. So what I'm going to do here, I'm going to go to my host machine. Let's see here what I'm going to do it. I have here the SDK installed. So I've just built the SDK. I'm going to search the SDK script. Then I'm gonna here list to see if I have the core dump. The core dump is there. I'm gonna copy to my machine the core dump 303. Then I'm gonna change to my user the core dump. Then I'm gonna go to the sysroot directory of the toolchain of the SDK. Then I'm gonna search for the binary with debugging symbols. It's there, my host machine. Then I can just start the GDB from my cross compiler, from the SDK, TUI mode, the binary with debugging symbols, and the core dump. Then the same result. So what I'm doing here in the host machine. I just want to do one more final demonstration because we are kind of out of time. Very quick. What if I want to do step-by-step debugging, right? I can do the same here. I can do step-by-step on the host or on the target, and that would be basically the same thing. I can show here the local.conf. That's basically what I already discussed in the presentation. So if I want to do local step-by-step debug with GDB, I will use the same flags, but one additional flag. Since I want to do step-by-step debugging, it's important to build the application without optimizations, or we're gonna have problems doing the step-by-step, run the code step-by-step. So enabling the debug build flag, it's important if you want to do step-by-step debugging. Now, if you want to do remote debugging, you will also need to enable the GDB server on the target. So you run the GDB server on the target, and then on the host, you just run the GDB client from the toolchain. I think we're out of time. I hope you enjoyed this presentation. And yeah, I'm open for questions here. I don't know if you have time or on Slack.
Well, we do have 5 minutes if you want to, if there's something
Great.
you can do in 5 minutes,
Yeah, we can do. I don't know. So should I do another hands-on or
Sure,
answer
please.
questions? Yeah,
No, that'd
let's
be great.
do it. Yeah, let's do GDB remote. Let's do local GDB debugging and then remote GDB debugging. So I'm gonna use the same problem here with fpink. How would local GDB debugging work? I'm going to the source code of the application that I installed in the target, and I'm just going to start GDB. So GDB, TUI mode, and the fpink application. And we are there. We can see here, hopefully you also can see that GDB was able to load the debugging symbols, right? Because I installed the package with debugging symbols in the target. And see that I'm already doing all of this in the target. And now I can, for example, put a breakpoint on main and then run the application. So I can run here the application, run -c. Then we are on main, and then I can do step-by-step execution. Yeah, it's a little bit messy because of the TUI mode and any curses here, but let me do a continue here so we can Control L, yeah. And then we can see that we got here the segmentation flow in the target. Now let's do the same thing in the host, so remote debugging. So for remote debugging, as I mentioned, I need to install GDB server on the target. So let's do this. Actually, I have already done this, so I'm gonna start GDB server on the target. So GDB server, I'm gonna listen to this TCP port 1, 2, 3, 4. I'm going to debug this application and with these parameters, right? So now GDB server is waiting for a connection, so we can start debugging this application. Now I'm gonna go to the host machine. I am already in the SDK directory. So I'm gonna just source the SDK script again. I'm already in the SDK directory. Let me find the application with debugging symbols again, and then it's just a matter of starting the GDB client from the toolchain with the applications with the debugging symbols, right? I'm also enabling here the TUI mode. Great. So, but what happens right now? We're not running the application yet. So the first thing I'm going to do is put a breakpoint on main. And then I'm going to connect to the target. So there is a command on GDB, target remote. And then I'm going to give the IP address of my device and the TCP port. And then we should connect to the device. And let's do a continue. We can go to the device terminal. We can see that we started the remote debugging session. I'm connected, but nothing happens yet. Now I can just continue the execution until we hit the main function. We can see here that GDB was able to load the symbols from the directory inside the SDK. And now we are in the main function, and then we can do step-by-step debugging of this application, but running in the host. That's usually what I prefer to do because I mean, we have more resources on the host. We can do anything on the host, but the target usually is more limited, right? I can continue with execution until we hit the segfault issue. And yeah, the same bad pointer issue again.